inform the participants. So, can we start now?
Sure, sir. Just give me a minute. I'm just sharing my iPad screen, and then we can start.
Sure, sir. Meanwhile, I will inform candidates, the participants.
Oh, sure, sure. Okay, Vikas sir, my screen is visible. We can
Yes,
start
yes, sir.
whenever you say.
I have just informed the participant. Uh,
Okay, let's wait for a couple of minutes. Meanwhile, in case if any of you have any specific queries with
yes.
respect to my previous session, you can ask in the chat box, so I can address them. Okay, so one of the question is which application uh, did you work on using graph neural network? So if I kind of talk about applications, then like I mentioned about autism detection. So one of I worked on this particular variant of graph neural network, one can say, to improve the performance of autism detection. That is medical domain, one can say. Apart from that, in the previous class, I had also mentioned about floor plan classification problem. That is from architecture domain. Apart from that, a few of my students are also working in the domain of kind of NLP, one can say, where we kind of try to try to do sentiment analysis, but again with the help of graph neural network. So these are a couple of domains on which I am working. Apart from that, the primary focus of my research is mainly on kind of improvement of existing graph neural network framework, and that domain is kind of generic. So once we have enhancements in terms of let's say instead of GCN, if we have some enhanced version of GCN, let's say GCN dash, which is powerful as compared to GCN, then it's a kind of, one can say, more meaningful contribution, because now wherever GCN is there, it can be replaced by GCN dash, right? So that's the idea of my research, where we so if I tell you very kind of intuitively, then the idea is usually whether it's a machine learning or deep learning, we split our data set into training and testing. But we do this randomly. There is no criteria, right? Let's say if we do this split of 70/30, there is no criteria that how this 70 data points will be selected. So in I guess in 3 to 4 different kind of variants of GCN, what we did, instead of training data points randomly, we kind of recommended some kind of algorithms which characterize this particular process more algorithmically. So the idea is, instead of selecting this 70 points randomly, if the performance in the testing will improve if we give structurally rich data points in the training, right? So the if I take analogy in terms of our classroom, then the idea is let's say out of 100 hours of teaching, 70 hours of teaching is kind of interactive, where you provide material to your kind of students. But what material you provide, that also matters, because let's say I give some material which is outdated, versus if I give question papers of, let's say, last 5 years and discuss about them in the classroom, then it's very likely that in the second case the performance may improve slightly, right? Because now I'm giving more relevant kind of data in training, something like that. Not exactly, but what I'm trying to give you is intuition. The idea is, if we give better training, then the result will very likely to improve in unseen data, which is test data. So instead of selecting this data points randomly, in what we propose is, instead of this, we characterize, we give scores to each of the data point based on some structural properties, like centrality measures, like between the centrality, clustering coefficient. These are kind of network parameters. I'm not going into the details, but the idea is, the traditional graph neural network or deep learning or machine learning methods select 70 of these data points randomly, but I assign some kind of scoring mechanism to each of the data point, and then I will then take top 70 data points based on that particular scoring criteria to my training, and then we have seen significant enhancement in terms of results, right, by doing this simple change in training mechanism, right? So that is kind of one can say centrality based graph neural network, which is a more kind of generic contribution and not dependent upon any specific type of application, of course. And with respect to autism detection, we have used the famous kind of open source data set, which is called Abide data set. It's a very standard data set. Most of the times, whether you apply deep learning or machine learning, people usually prefer, because in medical domain, there are a lot of issues associated with data. So we had used this Abide data set. Okay, all right. So I guess, Vikas, sir, if I'm not wrong, we can start now, right? Because it's already 6:33. So formally, I guess we can start now.
Yes, sir. Yes, sir.
Yeah, sure. Sure, sure. Okay, so before we go into the details, let me quickly recap, right? Let me summarize what we have discussed in the previous class. So if you can recall, then we had started with small word property, right? So the idea was, if I just write it down, the summary of it, then small word property says that on an average, right? Sorry for this auto, instead of it's correcting, it's auto incorrect, I must say, in this particular case. But any case, anyway, so in small world property, we have observed that on an average, if I talk about average path length between any two person on Earth or on Facebook or any type of network, then it's in this particular range. Like I can say 4 to 10. It's very less, right? So that's the idea of small world property. Apart from that, we had also talked about clustering coefficient, if you can recall. So the idea of clustering coefficient is how closely your neighborhood is connected. So let's say if you have three friends and if all of them are also friends with one another, then clustering coefficient is, in this particular case, it will be one. In this particular second case, where none of your friends are kind of connected with one another, then it will be zero. So it will be always in the range of 0 to 1. And this value is also relatively very high in real world networks. So even if we get clustering coefficient of zero point 0.2, it will be considered as high. Why? Because 20% means, if you look at into, because this is with respect to ages. Clustering coefficient is equal to zero point 0.2. That means in your neighborhood, there are, uh, let's say, 100 different ages are possible, and out of those 100, 20 ages are actually present. So potentially this 20 ages may connect at most 40 people, and this is a very big number, right? I hope you can imagine this, what I'm trying to say over here is. And can anyone guess how many vertices are sufficient in your neighborhood to have 100 possible ages? Okay, I'm repeating one more time. What is my question? My question is, how many friends I must have so that, let's say, I can have one, two, three, four, five, six, up to, let's say, X number of friends. Friend one, friend two, friend three, up to, let's say, friend X. Can you give me value of X such that in my neighborhood approximately around 100 edges are present? If I'm taking X is equal to 4, then I can take 4 choose 2, and the number of edges will be only 6. So 4 won't work. 4 is very less. So you have to come up with slightly bigger number. Let me try with 10. So 10 choose 2, right? 10 into 9 divided by 2, again 45. This is also not a number which is close to 100, I can say. So 10 also won't work. So can you guess what should be the number with respect to X? I'm just trying to explain this idea why zero point 0.2 is considered high. So that's why I'm taking this example. So what do you feel? What should be the value of X? Any guesses? You can simply apply this formula, right? So basically what we are trying to do over here is, I can pick any of my two friends, right, and connect them. Okay, so that's the maximum possibility, and I'm giving you this number. X choose 2 is around 100. So what should be the value of X? It's a very simple question, I can say. I can't simplify further. Right? What do you feel? What should be the value of X? That's the question. Can I take 20? 20 into 9 divided by 2, so it's 190. Okay. But still, it's more than, I can say, 100. So let me take 15. 15 times 14 divided by 2. What will be the value of this? Can anyone tell me? Okay, so it's 105. So roughly, I can say 15. So now let's continue this analysis. So now we have considered a specific case where, let's say, one particular person is extrovert and he has 15 friends. So with 15 friends, okay, so let's say this is you and these are your top 15 friends, okay, F1, F2 up to F15. So with respect to 15 friends, there are 15 choose two connections are possible. Okay, and I am saying roughly 20% of them are present. So let me take that particular number around 21 or something like that, right? So then the overall ratio will be around zero point 0.2 only. Okay, so whatever number I get, okay, whatever in this particular case, it's around zero point 0.2. So now, if you analyze this further, then you will be able to guess why it's called still high, because 20% of ages are actually present over here, right? So even though 21 ages are there, it has potential to, if the endpoints are kind of distinct, right? Then it has kind of potential to connect around 10 different friends at most, right? So which is again a very big number because you had total 15 friends only. Okay, so because of this kind of intuition, even if clustering coefficient of 0.2x considered as high, right? Even if you don't understand this, it's fine. Mainly, all I wanted to convey is even with this value, like zero point 0.2 is considered high with respect to clustering coefficient, and for most of the real world network, the value is high. And then we had also analyzed third more parameter, which was again corresponding to nothing but we talk about giant component or connected component. So most of the times you will observe that all the nodes of our network will form a connected component, right? And that's the majority of nodes. Usually 90 to 99% of your nodes will form a big connected component. Okay, right. So these three properties were important. Now, if you can recall, then we had already connected the first property when I had give you the brief intuition about graph neural network. So the idea was we are going to have embedding. Embedding is nothing but representation of my kind of node, which will kind of capture all the properties of the node apart from its neighborhood property, right? And there, if you can recall, then the idea was we go up to only 2 to 3 layers in the case of graph neural network. So why we stop? Why we don't go even further? Because if we go even further, then effectively we are going to cover the entire graph. So it's just because of small world property, I can just write it down how it's related with architecture of graph neural network. So that is directly kind of related with, I can say, our length or height of computational graphs. Height of computational graphs in our graph neural network, right? Okay. So that's how we had seen that these two concepts are related. Apart from that, if I quickly summarize what all the things are required if someone wants to apply graph neural networks, then the first one is nodes. You have to identify what will be the nodes of your graph. Second one will be ages, right? Ages may sometimes it will be trivial, implicit. Sometimes you have to define some rules, right? For example, I have mentioned about architectural problem of floor plan classification multiple times. So there, how ages will be constructed, that I had to decide, right? I had to come up with some equation which makes sense to me intuitively as well as in terms of construction also, right? Whether it follows these properties or not, that we have to verify. But that's the idea, right? Sometimes, like for example, Facebook, it's very easy to and intuitive to whether the age will be there between X and Y or not. If they are connected on via friendship relation, then we can put an age. Otherwise, we can't, right? But sometimes, like I mentioned about this, let's say this is one block of let's say floor plan. This is another block of floor plan. They are far apart, but still whether to put an age between them or not, right? We have to come up with some kind of criteria. One can come up with this kind of criteria, whether they are sharing a common wall or not, right? So that may be one criteria. One can come up with kind of distance between centers of this two, right? Whether it's less than some threshold or not, then they can come up with some kind of criteria or threshold, that if distance is less than threshold, then it will be created. Otherwise, it won't, right? So it's totally up to you. And therefore, it's a very creative field. It's not like that for given data, you can generate just one graph. So this itself is a challenging research problem to come up with a good graphs which gives better results for given for the underlying graph neural network, right? So it's a very interesting domain of uh, uh, kind of possibility with respect to research. Okay. Third one is I haven't talked much about this particular thing, but it's obvious, like, and you can guess it correctly, that we also require features of each and every node. And if you don't have features, then you can use one hot encoding. But without features, the graph neural network does not work, right? So if I summarize this in terms of visual representation, then I need something like this, right? So let's say this is my graph. Then first I have to draw like this, right? And I can't randomly draw. Of course, I have to set up some rules. So I have to identify some rules. What's the creation criteria, right? So age creation criteria you have to fix. It's very crucial. Okay, how you are going to create, right? An age, that criteria you have to kind of decide, right? You have to come up with it, right? And it also depends upon which research problem you are trying to address with the help of this graph, right? So it's freedom is with you, but you have to ensure you do it properly. That's the age creation criteria. And apart from this, right, let me use some different color. So we have identified nodes, then we have created ages based on some age creation criteria. And the third thing is with respect to each kind of vertex, I must have some feature vectors, right? And feature vector must be of same length. So let's say I'm having 5 features for vertex B, then the 5 must be consistent with respect to all the nodes, right? So once we have these things ready, then only we can apply graph neural network, right? So I'm repeating one more time: nodes, ages, and then I have this kind of feature vectors: feature vector of B, feature vector of C, feature vector of A, and feature vector of D, right? Like that. Okay. So these things are essential. So now I guess I can talk more, right? I can continue. Okay, fine. So we had seen, I guess most of these things were covered, right? With respect to this setup, the technical aspect was pending, right? How the kind of actually computational graphs behave, how they kind of capture neighborhood information, right? I had also talked about aggregation function, if you can recall. So those things are there. These were some of the important applications which I had highlighted. Apart from the important task of node classification, link prediction, right, community detection, right? So all this kind of tasks you can accomplish with the help of graph neural network. And the fundamental idea of graph neural network is we are going to map vertices like this, right? So we are going to have one feature vector representation for vertex U as well as V, right? And likewise, we will do this for all the nodes, but we have to ensure that whatever similarity between U and V is there, the same similarity must be also kind of persist in the this embedding space also, right? So whatever vectors we have, the similarity between those vectors must be aligned with similarity between our original nodes. So this we have to ensure why we do this kind of mapping, right? So this is the essential thing or important thing. Okay. So now, if we again one more time look at into this, then this is the traditional deep learning framework which we already know. Usually, we have this kind of fixed structure like images or text, and then we in the case of CNN, that we have this kind of layers where initially we try to kind of find out some uh, low level features, then we combine those features, and as you can see, initially there are patterns of local contrast, then we are talking about face features, and finally we are talking about face, and then finally we get output. That's the idea. But now unfortunately our networks are not regular like images or text, so we can't apply this method directly, and we had talked about this earlier also. So this was the idea of convolution, right? And hopefully you know about this. But even if you don't know, I can give you a one little example so that you can understand what it means. So the idea of convolution you can relate easily with this kind of example. Let's say there is one room, and in this room there is one key, and this key is very much important for you. Okay, so my drawing is very bad, but let's assume this is key, but the key can be anywhere. So what you do usually is you divide your room into kind of portion. First you will say, let me focus on this region which contains sofa, and let me see whether my key is over here or not. And in your image, in your brain, you have image of this key, right? So you constantly try to kind of compare whatever you see whether it's key or not, right? Subconsciously you are doing, but you are doing still. So okay, sorry. So once you complete this top left to top right comparison, then you go to the kind of second segment of your room, and there again you repeat the same idea. Let's say sofa is done. Let me check out the chairs, and then you look for the remaining portion of the room. So now, since you have scanned your entire room from uh, left to right and top to down fashion, irrespective of where your key is, it's certain that it's you are pretty sure that you will be eventually able to find it if it's within the room, because in your brain you already know how your key looks, and that's why you will be able to find out for sure. The same idea is there in the case of CNN. Instead of this brain image of key, now you have this kind of filter, right? And you kind of there is a window, right? You kind of rule this particular filter from left to right, top to down manner, right? So irrespective of where this particular pattern is there in my image, the filter will be able to detect it, right? So that's the idea of CNN, right? And so therefore, it's a kind of location invariant also, right? It doesn't matter whether your pattern is towards the left side of image or right side of image or in center, because you are going to scan it. So eventually you will get it, right? So that's the idea of CNN. So if we try to kind of map this idea in the context of graph, then we can say we are doing something like this. Let's say whenever I put this particular pattern on let's say top left corner of my image, then I can say I am giving a decision for this particular middle pixel value. Okay. So in terms of graph, I can say I am giving decision for this middle node. And in some sense, the filter is taking values from all its neighbors, right? So the same idea we will kind of enhance when we talk about graph neural network. So the idea is same. We are going to take instead of pixel values, we are talking about features of the node. And what we are going to do is we are going to take this information from our neighborhood. And as I have mentioned earlier, of course, I have to give some weightage, right, to the node itself, right? Let's try to again reconnect with the example which I had given you in the earlier talk. So the idea is graph neural network. You can consider like this: you are CEO of a firm and you are taking interviews, and how the particular selection will be done. The criteria is you give some importance to performance of the node itself, how the candidate is performing. You give, let's say, 80 to 90% importance to that performance itself. And then, so that thing is represented via self loop. So self loop is nothing but you are giving self importance to features of the node or candidate itself. And then you give some importance to some weighted kind of importance to aggregation of neighborhood feature also, right? So that's the idea. Okay, fine. Okay. But the issue is, as we know, the structures are not regular. And the one more issue which I had discussed in detail in the previous class, I can briefly revisit it, is nothing but node invariance feature, right? So the idea is the graph is same, but the labeling is different, and labeling is different. So therefore, our adjacency matrix representation is different, right? So because of this, what will happen? That my input will change, and for the same graph I will get different type of output. So therefore this should not work, and ideally my representation must not be dependent upon order plan or labeling plan. So this property is called permutation invariance. Irrespective of how I'm going to label my graph, my final representation must not depend upon that order plan, right? So that's the idea, right? So if, as you can see, graph and node representation should be same for order plan one as well as order plan two. So basically, there are two types of tasks when we talk about graph neural network. Traditionally, most of the times we talk about node representation only. But in some special cases, like for example, I would like to, the entire molecule is represented in terms of graph. So there, I may be interested in graph representation also. So in graph representation, I will get a singular matrix, a single vector, I can say. A single vector will be there, which will represent the properties of the entire graph. Whereas in the case of node representation, my focus will be on properties of the node only, right? So these two terms are different: node representation and graph representation. But for both of them, the important property is permutation invariance. Whatever your graph is, your final representation must not depend upon your nothing but node orderings, right? So that's the idea. So formally, we can also say it like this: whatever vector we are getting after mapping. So let's say my final vector is in d dimension RD. I have a vector of length d. Then whatever mapping you have with respect to plan one, the same mapping you must have for plan two also, because both the plans are corresponding to nothing but same graph, right? So that's the whole idea, right? For two order plans, output function should be the exactly same, right? So that's the idea of this particular term, which is called permutation invariance. Okay, fine. So I'm not going into further details now. And similarly, there is one more concept which is called permutation equivariance, right? So let's try to see what it means. So now we will talk about only node representation, not graph representation, right? So you can see the difference now. In terms, when we talk about node representation, for each node we have d-dimensional kind of vector. So as you can see, there is a vector of m cross d, right? So m nodes we have, and for each of the node we have uh, like vector representation of length d. And now, as you can see, the key idea of permutation equivariance property is for two order plans, the vector of node at the same position must be the same. Right. So as you can observe that here there is one vector and this is the representation. Here there is one node and the its corresponding representation. And here the node name has been changed, but the corresponding vector representation is as it is, right? So that's what the permutation equivariance property means. Okay, fine. So now let's go further, right? So as you can see, the main idea is whatever graph neural network method which we are going to see and utilize, they follow both of these properties, right? They are permutation equivariance, right, and as well as uh, invariant, right? Both the properties are kind of being satisfied in graph neural network. And the resolution I've already mentioned, the idea is aggregation function. And in the very first graph neural network framework, which is nothing but graph convolution neural network, the idea is we are going to use aggregation function, which is called nothing but average, right? So average of you take last three matches, or maybe let me give simpler example. Let's say average of 531 is equal to, I can say, average of 135. This is nothing but summary of whatever I have discussed in the last 4 or 5 minutes, right? So the idea is it does not matter, right, whether I write one first or three first or five first. The average of three numbers will be same. Right? So this type of function will help us in capturing node, uh, not just capturing in terms of aggregation, because we are combining the features of the neighborhood intelligently with this kind of function, which are called aggregation function, and they do not depend upon orderings. And this is the proof why we need this. So as you can see, this is nothing but our normal multi-layer perceptron, and you can see the inputs are exactly same. Here, if you observe carefully, just ordering of input has been changed, and you can notice there is a change, significant change in my output also. So that means this is nothing but just one proof to showcase you these two properties are extremely important, and without them, we can't have graph neural network, right? Because if you consider any graph, for the same graph, n factorial different representation are possible, and you will get n factorial different answers for the same structural graph. So which is not desirable, right? Then your model is useless. So therefore, whatever we are going to propose, it's independent of node ordering, right? So as you can see, the traditional approach, right? So usually we are lazy and we don't want to do any new work. So the question was, can we replace our image matrix with adjacency matrix and just append some features, and then we can just directly flatten this or entire array, and then apply artificial neural network or convolution neural network, and then we can say this is graph neural network. Then this solution won't work, because the reason I've already mentioned, for the same graph, you can have different adjacency metrics, and then your final answer depends upon node ordering, which is wrong. Okay, so you have to every time train your model, right? So this is not a solution at all, right? So therefore, this won't work. Okay, fine. So there are other issues also, right? So as you can see, node invariant to node ordering. No, one more issue with this solution is not applicable to graphs of different size, because you have fixed the size of your matrix, right? So you can't change it. So this solution won't applicable to different size. Number of parameters are also more, right? So there are a lot of issues with this approach. So therefore, this won't work. And now we are ready to understand the proposed framework of uh, GCN, which is Graph Convolution Neural Network, which is the first graph neural network model, right? So before I talk about it, let me just briefly tell you about graph neural network frameworks. So broadly, there are three different graph neural network frameworks. The first one is GCN, which is called Graph Convolution Neural Network. The second one is called GATE, Graph Attention Network, and the third one is called Graph Sage. Right. So here SAGE stands for S stands for sampling, okay, and age stands for aggregation, right? So it's sampling and aggregation based approach, right? But the core idea of all these three are same, right? So once you understand kind of graph uh, convolution neural network, then you will be able to easily kind of not only understand but implement the rest of the two models also, right? So it's important to understand the fundamental graph convolution neural network in detail. That's why. Okay. Because not only you are understanding the GCN, you are also understanding core aspects of gate as well as graphs. Okay, fine. So setup is ready. You already know what we have. We must have our vertex set. We must have our adjacency matrix. We must have features, right? So for all the nodes, we have feature vector of size m. Right? Usually in graph theory, we use m for ages, but here I'm using it to denote length of feature vector. So just remember it that m is nothing but length of feature vector. Okay. So these things we have, right? And usually this feature vector are given with respect to given data set. If it's not, then you can also generate them, right? For example, let's say you are taking some research papers, then you can generate feature vector like this, that some keywords are there, let's say machine learning, deep learning, right? So if machine learning word is present in the paper, then I will put one over here. If it is absent, right? So sometimes it can be just word vector also like this, right? Whether the word is present in the underlying document or not, right? And document is represented by node, right? So like that. And some other cases, right? It's obvious, right? For example, you get the entire user profile, that what was the activation year of the profile, how many friends of underlying person has, how many followers are there, right? So on and so forth, hobbies, interests. Similarly, for biological networks, the feature vector will be different. Like for example, in the case of autism, it will autism detection, right? It will be of MRI data set, and the reports of MRI will represent nothing but feature vectors. So depending upon your problem, you can have different types of features, but you have to ensure that you have some features at least. If you don't have, then finally you can use one hot encoding also, or some kind of constant vector also, because without features you can't apply this method, right? So you must have graph, and along with graph, like I mentioned earlier, with this graph you are also having this kind of feature vectors. Okay, so that's the only thing you have. Now this is the core idea how this model works. So first, let's say I am generating some kind of embedding or vector representations for this particular node. Let's say I. So then I need to consider all the neighbors of node I, take some information from them, which are information is nothing but their features, and I will apply some aggregation function, which is nothing but in this particular case averaging. But we won't stop here. We go one more step, right? So we'll go up to this green kind of points, and they also kind of contribute. And the process which I have explained, the flow will be exactly opposite to what I have said. So the process will start not from I node. I is my target node. The process will be started from this outer green node. Green node will communicate to blue node, and blue node will finally communicate to I node. Right. So we'll go like this. Instead of kind of top down, it's basically bottom up approach. First, this nodes will give information to this, and then this nodes will give information to this, and finally the embedding for this node will be generated. Okay, so this is the idea. Okay, so concretely, if we see, then let's consider this particular example, and I want to generate some representation of for this, let's say this particular node, which is, let's say, node A itself. Right. So now what's the idea of computational graph suggests that if you want to generate some kind of representation for node A, then you have to consider its neighborhood. So what are the neighbors of A? If you notice closely, then B, C, and D, they are neighbors. So B, C, and D, they are here. Now we have to go one more step, because in GCN, ideally the height of this computational graph is 2 at least. So now we have to go one more step. So now what are the neighbors of B now? So as you notice, neighbors of B are A and C. Okay, so A is here, C is here. Likewise, other neighbors are mentioned over here. But now the question is, you are trying to design some representation of A, and in which you are again using representation of A, right? So what's the difference between these two now, right? How can you generate something, right, as an output where you are using the same quantity as an input of the process, right? So this is kind of paradox. It's a recursion without base case, right? So the idea is these two things are different. Here, whatever is written from here, I'm going to start my process. Do you agree? Because, like I mentioned, the process is bottom up. And initially, I don't have anything but feature vectors. So these are nothing but my feature vectors. So this is f of a, and this is x of a. X of a is nothing but my final embedding vector. So embedding vector and feature vector both are different. So this is what I will get in as an outcome of this process. And these are nothing but my initial features, right? So that's the difference between these two. Okay. And the flow is like this. So in between there are some boxes. What is the purpose of what is the purpose of this box, right? So they are nothing but neural network. They will try to learn weights. Weights are corresponding to how much importance must be given to neighborhood. That's one thing. And apart from that, they will also perform the simple thing of nothing but averaging, right? So those two things will be done by them, right? And this kind of computational graph will be generated for the all the nodes of your given graph, right? So computational graph is not like that you will generate it for just one special node. It will be generated for all the nodes, right? So okay, fine. So far so good. And the biggest advantage of using this technique is the whatever weights we are going to achieve after kind of training, those weights are kind of shared. So what I'm trying to highlight over here is, so let's say the model is telling me to give 83% importance to features of the node itself. So then that 83% will be consistent with respect to all the nodes, right? And then it's saying that give 10% importance to neighborhoods. So then that 10% will be true, also true across first layer of all the computational graph, and remaining 7% to all the nodes of second layer of the all the computational graph. So in other words, these parameters are shared, and the biggest advantage of this mechanism is the result will be extremely good for unseen data also. Because now if new data comes, I don't need to retrain my model. I can just directly say, okay, something else is coming up. I want to generate its embedding. I will just say give 83% importance to yourself, 10% to neighborhood of your one hop distance and take average, of course, and 7% to neighborhood at layer 2. And then the embedding will be ready on the fly, right? So that therefore, for many of the problems where data is kind of incomplete of or unseen, then this kind of graph neural network model offers better results, right? So that is one more advantage. Okay, fine. So if we see this formally, then the terminology which we are going to use is it's different from what I have mentioned you for the explanation purpose. The idea is we are going to use the capital X. Okay, so as you can see, the feature vector for my node at layer 0 is nothing but x suffix u. If I'm talking considering node u, then input feature will be x suffix u. So for example, here I am going to say x suffix a, x suffix c, so on and so forth. Right? So that is nothing but my initial feature. This is what kind of if you are confused, then this is nothing but whatever is being provided by the data set, right? Or whatever you have come up in terms of features, those things are initially over here. Now, what we are going to do now, as you can see, these boxes will perform only two things. They will average out the whatever the features are there in the neighborhood, and they will also apply neural network. So now let's understand this particular slide, and then you will be able to appreciate this architecture very nicely. You will be able to understand the fundamental of this. So now the terminology is slightly different, as I mentioned earlier. The change is I am saying that initial feature vector is X and the final embedding is Z. So remember this. X stands for initial, and this is nothing but vector, And the final embedding which I am going to generate, embedding is nothing but based on which I'm going to give all kind of my prediction, whether it is node classification or link prediction, whatever it is. The key is there is one important vector which captures all the structural information about the node. Also, its features and features of neighborhood and neighbors of neighbors. That is nothing but my Z. So Z is my destination where I would like to reach. uh, X is nothing but from where I am starting, and in between, whatever representation of node is there, I'm going to use this particular terminology. I will say representation. H stands for intermediate representation or hidden representation. In suffix, whatever I write, that is nothing but name of the vertex. For example, I will say I stands for, I'm talking about intermediate representation of node I, and the superscript will represent how many layers I have already covered so far. Right? So if I say HIK, that means I am referring to nothing but hidden representation or intermediate representation of node I after k layers. And usually, in the case of our graph convolution neural network, value of this capital K, right? For how many layers you will repeat this particular process? It's usually two. So now let's understand this process. It's obvious that for vertex V, if you haven't done anything, so you are at zero level, then layer zero, then your intermediate representation is nothing but your initial feature vector. So HV0 is nothing but X of V. This is obvious because you haven't done anything. So your intermediate representation is nothing but your initial representation or initial feature vector. So therefore, HV of 0 is equal to X of V. And hopefully it's very clear, right? So this is what we are doing. Okay. Now, if I okay, so before coming into this particular important equation, let me give you intuition here. So what we are going to do now, basically, we are doing only two things. We are for each vertex, we are going to give some importance to itself, and that particular importance will be denoted by self loop. And let me call this particular self loop as nothing but, let's say, beta. So I'm saying that beta importance I'm going to give to the node itself, and then I will consider neighborhood, and then I will take average of features of all of this, and then I will give some kind of that we can use some other symbol, let's say W times whatever we get as average of this neighborhood. That W parameter will be also, these two parameters will be learned by nothing but our model, right? So these two parameters are important, and let's see how this information is kind of being conveyed in this equation, right? So let's see. So as you can see here, the okay, sorry for this. So if we go ahead and okay, I apologize for this extremely quick revision in some sense. Okay, so okay, so maybe I can go via this so that we can reach there very quickly. Okay, fine. So here, as you can see, this is nothing but my self loop thing because I'm talking about representation of vertex V at layer K. So this is like I'm talking about some intermediate representation for some candidate. So for that particular candidate, I must give some importance to that particular candidate himself. So at layer K, I'm already done with layer K minus one. So for the same vertex, I can take its representation, which is available with me, and then I can give some self loop importance, which is beta importance to this particular intermediate representation. So that is what written over here, as you can notice that I am giving beta importance to node itself, whatever representation of node available with me, right? At previous layer, I am giving beta information importance to that, and then remaining importance w suffix k importance I'm giving to neighborhood, right? So I will go to the neighborhood and I will take average of that representation, and then I will apply w times that average value importance to that neighborhood. So let's see how it is being done. So I will consider all the neighbors of node V, and then what I'm doing, this is nothing but average. If you notice it carefully, I'm just applying sigma. Sigma means summation. I'm just doing summation of all the representation of node U at layer k minus 1. And after doing summation, I'm just dividing it by total number of neighbors of node V, right? So this is nothing but average, and this new thing, which is nothing but average, I'm just multiplying it with W, and then I will be able to generate this intermediate representation. And this is quite logical also, because I'm increasing the value of k like this. Initially, k is equal to 1, then 2, and then 3, and so on and so forth. But we will usually stop at 2 only. So the idea is, let's say value of k is 2. Then I want HV of 2. For HV of 2, I need, if you follow this particular equation, then you need HV of 1. So that means I can't directly go to HV of 1, HV of 2. I must have value of HV of 1 also. So it's obvious that this equation will go like this. Initially, I have ready with me the value of HV0. Now I will calculate HV of 1. For HV of 1, only HV of 0 is required. So that is done over here, because this is nothing but, if you look at into this, then k minus 1 will become 0 over here, right? So HU of 0 is available with me, because this is true for all the vertices. So this is with me. Similarly, HV of 0 is also available with me, right, from the equation 1. So now I can compute HV1. And once HV1 is ready, then I can compute HV2. When HV2 is ready, I can compute HV3. Likewise, and once HVK is ready, I can done, right? And that is nothing but my embedding. And if you look at into this by some other logic, then you can say that first all these things, let's say all these green vertices will give information to this vertices, and then all this will give information to this, right? So those things are now making sense, because now this is k is equal to 0, this is k is equal to 1, and this is k is equal to 2. Likewise, it will iterate, and then finally you will be able to generate representation for all the nodes like this, right? So it's very easy and intuitive. This is how this is the core concept of graph convolution neural network. And I guess this is a good time that I also talk about kind of implementation part. So now I am sharing my other screen. Okay, so let me kind of share it. Okay, so hopefully my screen is visible. So now I'm talking about implementation part. Okay, so the most of the times. Okay, fine. So it's visible properly. Okay, fine. So most of the times, whenever we talk about graph neural network, we usually start with this Cora dataset. It's a very simple dataset. Let me showcase this particular dataset so that you can easily relate with it. So it has two files. The first file is called Cora underscore sites. And from the citation name itself, you can imagine it's nothing but it's a data set about research papers. So nodes will be represented sorry, the research papers will be represented by dots or nodes. And if a particular paper is citing another paper, then we will just connect those two papers. Don't worry about the direction. Connection matters for now. Okay, so now okay, so let me just explain briefly about this data set, and then we will see the files. So as you can see, the data set contains 2708 publication. So you can guess how many edges will be there. No, sorry, this is corresponding to nodes. Total 2708 nodes will be there, because those are corresponding to our research papers, and 5429 links. So these are corresponding to nothing but my ages. And now nodes, ages, those two are first two requirements. The third important requirement is you must have feature vector also, right? Or features also. So for that, we have this 01 vector of length 1433. So it's very obvious that if word is present, underlying word is present, then we will put 1. Otherwise, we will put 0. Likewise, we have for each we have this collection of unique 1433 words, and we have this vector for each and every vertex of your graph, right? In this particular case, 2708. And this information is being conveyed via these two files. The first file I have already showed. Right? The first file is this core underscore sites, which has nothing but just list of edges. From list of edges, you can also construct list of nodes. So here it was very easy to construct graph. So graph will be anyway constructed just via this one file, but without features, we can't go ahead. So for that particular purpose, this is the important file which has feature vector also. As you can see, the 01 vector is there. It's a very long vector of length 1433. And then finally, towards the end, you can see this kind of labels also, since this is kind of supervised learning. And for each paper, its category is also given, whether that particular paper belongs to neural network or theory or genetic algorithms, probabilistic methods, case-based methods, so on and so forth. So now hopefully you understand the problem. The problem is we have to perform node classification. From the given data, we have to predict whether the paper or research paper belongs to right genetic algorithms or neural networks or theory, right, based on the features which we have available with us. And apart from that, we have this citation information available with us, right? So that's the setup. So now let's see how it has been done. I'm skipping the kind of very trivial details. Let me focus on the aspects which make more sense. So as you can see, this is a distribution that which papers, how many papers we have from the different domains, right? So on and so forth. One hot encoding is important because then only we'll be able to kind of find out what's the gap between what's the error, right, between our kind of prediction and actual thing. And then we ultimately we have to kind of bridge that particular error. We have to minimize that particular error. So therefore, one hot encoding is important. And now if you see the setup, then it's very beautiful, right? Because the idea is we know that towards the end, we need to kind of give result in terms of out of the seven class, which class we are talking about. So you can notice that towards the end, if you focus, then you can see this particular seven over here. The seven is very important because it represents that ultimately whatever embedding I'm going to get, that will be of length seven only. So basically, the after creation of computational graph, the vector which I am going to generate, which is called embedding vector, it will have length only seven, right? Which is very good because then I will be just apply softmax and will be able to get prediction. So it's the very first observation. Initial feature vector length. This is also quite important. As you can notice that initially I am starting with this big number, which is 1433, right? So I'm starting with this 1433 big number and I'm just reducing the length of the feature vector. But magically in between, I will ensure that whatever that seven value remains, those seven values represent the characteristic of my node, right? So that's the idea. And in between, you can see the structure is very much similar to your CNN. This is kind of your right. In the case of CNN, it was like kind of your filter size, right? Here it's called layer size, right? So it's 16 cross 16. Activation function value, drop out, right? All these concepts, I guess you already know, so I don't need to spend time over here. Softmax function activation, right? You know all these things, right? So implementation is not difficult thing. Right? The main part was that fundamentals, right? So that's why I spent most of my time over there. But still, I'm just showcasing you the key aspects of implementation also. So one more thing which you can notice over here is, as you can see, patience is equal to 50. So that means if after 50 iteration, if my result is not changing, then I will stop. So that is nothing but kind of my early stopping criteria. All of you know about this epoch, right? So epoch is nothing but corresponding to number of iterations, and will usually keep shuffle is equal to false because then otherwise the kind of our node ordering will change. So therefore, it's important to keep it false. Other things are very kind of trivial. Okay, so let me also share some of the notebooks so that you can appreciate it, and let me showcase some important results, right? Where you will be able to kind of appreciate the power of graph neural network. So what we have done over here is when how powerful our techniques are. Just to I'm talking about implementation part in a while now. This is slight diversion just to showcase you how powerful graph neural network techniques can be as compared to traditional machine learning. So the idea is many times we draw this kind of TSNE curves just to showcase kind of quality of our embeddings. So you can see, you can notice seven different colors over here, and those colors represent seven different classes of Cora data set, right? And you can see most of the points are close together, right? So the yellow, orange points are close, the green points are close, the red dots are close, right? So that means we are doing good. That the color represent the correct class of the underlying paper. So that means what we have done, we have classified the kind of research papers correctly, right? Most of the times, as you can see. And now, if I showcase you the fully connected neural networks result for the same data set, then you will be able to see the difference. This is the result of our standard artificial neural network. And as you can see, it's not doing good, right? So the representations are very kind of sparse, right? You can see many dots, many kind of green dots over here, whereas the actual location of them must be over here. You can see some misclassification over here also. The red ones are kind of painted over here, right? And you can't identify them properly, proper clusters as compared to this representation. So this is just to showcase how good the embedding representation of graph neural network as compared to normal traditional artificial neural network, right? Apart from that, the epoch thing, right? The implementation part is very much similar to your normal CNN. This kind of feel you get when you apply traditional CNN also, right? After every epoch, usually your accuracy will increase, loss will decrease, right? So those things you can easily see in graph neural network also, right? So as you can see, after 100 epochs, this is what we have got. And then we can also print this kind of classification report, right? And you can see accuracy is around 81%. Whereas in this particular case, if you just apply fully connected neural network, then you get very less accuracy of around 74. It's F1 score, sorry, of around 0.74, right? So it's a drastic difference in terms of even if you see in terms of epoch, then after 17 epoch, right? In this particular case, you can see the accuracy was very low, even though it was the number is also less, but still it's as compared to graph neural network, the results are not that good, right? So as you can see, the results of TSNE curves, right? I already mentioned about it, and there are a couple of different methods to implement this graph neural network, right? So some of them are mentioned over here. There are some important libraries which you can use to kind of implement this. So implementation is not difficult, and anyone can do it in the era of chat GPT. So I'm not or and large language models, of course, Grok or whatever, Gemini, right? There are many options which you can use to kind of just if you just want to play with initial versions of this code. So I'm not spending too much time on them. Stateless library is also there, right? So you can Keras, right? So you can kind of pick from there. It's not difficult, right? As you can see, implementation. This is with as you can see from the file name itself, it's clear that here the focus is on Stellar Graph Library, right? Using Stellar Graph Library, you can easily implement this graph neural network. So that's one way of doing it. If you without using Stellar Graph, also you can do the same thing. So in this particular notebook, I have implemented this without using Stellar Graph library, right? So there are many options, and you can explore on this. But one more thing which I wanted to highlight, and if you want, I will share this notebooks with organizers, so that you can kind of uh, done this graph convolution neural network at least for node classification tasks, so that you can gain some confidence. But apart from that, before I conclude my talk, I would like to highlight just a couple of things with respect to graph neural network. Apart from GCN, there are two more models. So let me just briefly give you insights. What's the difference between GC and Gate and Graph Stage? So in the case of Gate, the idea is it's called in let me just draw it and then explain you. Let's say you have three friends. And in the case of GCN, what you will do, you will take features of this three and then you will just apply average, right? So in some sense, you are giving same importance to everyone because you are just taking average, right? You are doing divide by three thing, just add and then divide by three. Whereas in the case of gate, there will be one more parameter, right? So you are going to give selective kind of importance. Now you will also learn about this hyperparameter, which is called alpha, right? You can have this kind of distribution. Let's say I will give 70% importance to features of this particular person, then I will give 20% importance to features of this particular person, and then 10% importance to feature of this particular person. Right? So you have this kind of additional weights associated with each kind of neighborhood, that neighborhood entity in the case of gate, which is called graph attention. From the A itself, it's clear that you are giving attention. So it's like selective neighborhood will get more attention as compared to others. So that is called that's the primary difference that we don't have much time, so I'm not going into the details of this, but the primary difference is this. Whereas in the case of graph stage, like I mentioned earlier, it's sampling and aggregation. So what is the advantage of sampling? Sampling means, let's say I have 100 uh, people in my neighborhood. So instead of taking features of all the 100, I will just take four as a representative. So instead of 100, I will just, so it's like, let's say, director of the institute wants to meet students of each and every branch, right? But practically it's not feasible because we usually don't have auditorium which can contain, like, let's say, thousands or which can accommodate thousands of students. So what usually we do is we take representative of each and every class and kind of arrange a meeting with the directors. So same thing is over here. That instead of kind of considering all the 100 nodes in the neighborhood, I will just select four of them. And same thing I will repeat with respect to layer 2 also. Instead of considering, let's say, all 200, I will just select only 20 representatives and so on and so forth. So if you do like this, then small world property won't harass us because now what is the idea? Because I'm not taking all the neighborhood in the consideration while computing computational graphs so that I can go up to layer 8 or 16 or even 24, right? So practically there is no restriction on the length of computational graph in the case of graph stage because of this sampling mechanism, right? So now you can go right up to, let's say, layer 16, 24, 36, and still get better results because you are getting some flavor from each of the nodes. And maybe the possibility that there are some dependencies which are kind of long range, which can be kind of obtained with the help of, or which can be captured with the help of this graph stage, right? So for unseen data and to capture this kind of long range dependency, graph stage is also a very good model, right? So hopefully that you got the basic idea about graph neural network and what are the key differences between these three models: GCN, graph stage, and gate. And now I guess I can answer questions if any. So again, I guess what you should do is once you at least implement the first task of node classification on Quora dataset, then you will feel more interested in this particular domain and you will kind of start to loving it, right? So these things are like better to be kind of practically done rather than just said, and hopefully you'll be able to relate with this domain. It's a very interesting domain and a lot of fundamental knowledge of graph theory that can be applied along with, so especially the graph creation part, it's extremely creative, right? So you can come up with your own rules and try and experiment. Yes, sir. I was just waiting for the question. Okay.
Sir, there are some questions, sir. Yes, sir.
Hi, yes, yes. Okay. In case of 1D data, how to use GCN as a classifier. Okay. So in the case of 1D data, so that means you are saying that you have just one feature associated with uh, kind of every uh, node, right? If I'm not wrong. So in that particular case, there are a couple of options. Either you can include some standard features like clustering coefficient or betweenness centrality or even just degree of the node, right? So you can come up with your own feature metrics also. It's what we had done in one of our research work was we had appended important clustering, not just clustering. In one of the case, we had included this closeness centrality as an additional feature of for each and every vertex of the graph, and then we could see that there was enhancement in terms of accuracy or whatever the underlying task was there for that. So that means, in summary, what I'm trying to say over here is, in many of the instances, you will feel that features are limited or it's not giving the results what you want. So it's a very good idea to include some of the important graph parameter values as an additional features for all the vertices, and then you can try again, and then your results may improve. All right, so that is one answer. And in case of 1D data, it may be the case that your kind of whatever you are representing, itself is kind of distinct values. Then you can also apply, I guess, one hot encoding. That is also one more possibility. So these things you can try. And also one more interesting research direction is, let's say, whatever problem you are solving, solve it the way you are solving without using GNN, but then club the embedding of GNN and see whether it can kind of enhance the results of the existing solution or not, right? So some kind of ensemble kind of thing, right? That is also kind of trending these days, where people use kind of embedding of GNN to improve the existing results with the existing framework. So that is also there. Uh, I feel that I guess some of you may encounter some questions afterwards also. So I'm also sharing my LinkedIn ID along with my email address, so you can connect with me afterwards also, and then we can discuss more. Okay. Any other questions?
I think there is no more questions, sir. Uh, so yes, there is no question, no query, sir. So let us conclude the session. So thank you so much, sir. Thank you so much for taking out the time for this session out of your busy schedule. And I hope this will be uh, this would have been a fruitful session for all of us, all the participants. So tomorrow, all the sessions will be mostly the application oriented. So I hope to see you all there, and it will start from 10 a.m. as it was already. So thank you so much, sir. Uh,
Thank you, sir. Thank you
we
for
are
inviting. Thank
concluding
you.
this. My pleasure, sir. Okay, so thank you all. Thank you all the participants who have joined today. Hope to see you tomorrow. Okay. Thank you, Asutosh. So we may